So, yesterday we discussed the tangent plane on a surface r equal to r of u1 u2. So, this is the parametric representation of a surface. So, I will recall certain basic things about the surface. So, if you look at the equation, you will notice that a surface is obtained when you consider a vector valued function on a rectangle. So, this rectangle is AB cross CD. So, this domain space of the vector valued function is the Cartesian product of two closed intervals, which will look like this. So, if I fix, so the equation becomes r of u1 u2. So, if I fix u1 equal to constant, if I fix u1 as a constant, then r becomes a function of only u2 and u1 equal to constant means a line like this. So, this is the line u1 equal to constant. u1 varies on the horizontal line, u2 is varying on the vertical line. So, the image of this line will be a curve on the surface, which is in fact a curve, and we call this curve as u2 curve. Similarly, when we put u2 equal to constant, r becomes a function of only u1 like this. On this line u2 is constant. So, the image of this line will be this curve over a surface. So, once again you get a curve over the surface, and this curve is called a u1 curve. And these curves u1 curve and u2 curves are called u1 curve and u2 curves are called parametric curves. So, we learnt about parametric curves in our last lecture. Now, if you consider the derivative of the vector valued function r with respect to u1, this derivative we denote by r1. And now, from the idea of u1 curves and u2 curves, you can realize that r1 is actually a tangent vector to u1 curve. Similarly, r2, which is del r over del u2, this is a tangent vector to u2 curve. Now, since u1 and u2 are two independent variables, we expect these r1 and r2 to be linearly independent vectors over the surface, and we say that r1 and r2 are linearly independent. This we can easily realize. Now, yesterday we found the equation of the tangent plane. Tangent plane by definition is the plane which has the highest order of contact with the surface at a given point, and its equation we found as at a point p0, its equation was r minus r0, r1 at 0, r2 at 0 equal to 0. So, these three vectors are coplanar vectors, whereas these two are linearly independent. So, what we observe from this equation that r1 and r2 are the basic vector which generate the tangent plane, because any two linearly independent vectors lying in a plane can be taken as a basis. So, r1 and r2, vector r1 and vector r2 can be considered as a basis of the tangent plane. There may be other basis vector also, but since they are natural ones, so we will consider this as a canonical basis of the tangent plane. basis of the tangent plane. Yes, yes, every plane is a vector space. So, this plane is also a vector space whose basis is R1 and R2. Okay. Whatever point you have chosen at P0 or some other point, whatever you like. So, this is the whole thing. Okay. Now, we also discussed some other type of equation. For example, we consider an equation of this type on R3, and we observed that this also represents a surface, and this equation of a surface is called the implicit equation. What happens is, if one of the partial derivatives f x or f y or f z is non-zero, then implicit function theorem says that we can convert this equation into an equation of the type z equal to f x y, if I assume that f z is non-zero. All right. Now, in this case, we can work out, we can see what are the basic tangent vectors R1 and R2, we work them out. We also found the equation of the tangent plane. So, we also noticed that the normal vector. Now, this you can see over here, R1, R2 are tangent vector. So, if you look at the cross product R1 cross R2, it is a vector perpendicular to R1 and R2 both, and therefore, it is a vector perpendicular to the tangent plane. At the point R0, we will say this is a vector. If I choose this vector at a point P0, then this is a vector normal to the surface. Normal to the surface at the point P0. P0 is RS0. All right. And if you want to find out a unit normal, we denote the unit normal by the symbol n. At a point P0, I will denote it by n0. So, this will become R1 at 0 product R2 0 upon modulus of R1 at 0 cross R2 at 0. This is called the normal to the surface at the point. Actually, it is normal to the tangent plane at P0, but we will be calling it a normal to the surface at the point R0. Okay. Now, if you are considering the implicit equation of the surface, then one can think of tangent plane to the surface represented by implicit equation. Tangent plane to the surface f x y z equal to 0. We derive this equation since I am considering tangent plane to the surface at a point x 0, y 0, z 0. Well, before discussing tangent plane, let me tell you what will be the normal to this surface. The normal to the surface in this case will be f x, f y, f z. Since you want unit vector, so it will be under root f x square plus f y square plus f z square. So, this will be the normal if the surface is taken into the implicit form. So, now I can think of the tangent plane at the point x 0, y 0, z 0. We worked out this equation as x minus x 0 into f x at 0 plus y minus y 0 into f y 0 plus z minus z 0 into f z 0 equal to 0. And this was natural also, because these are the direction ratios of the normal, okay, and the plane passes through x 0, y 0, z 0. So, this is a standard way also of writing the equation of a plane. all right. So, yesterday we worked out, while considering a tangent plane is the plane which has the highest order of contact. So, this is what I did in my last lecture yesterday. Now, we will be solving some problem based on these things. So, the exercises are given in these lecture notes. So, we will take up some of them, the remaining ones you can do by yourself. So, we have to find the tangent planes and normal vector for various surfaces. I will pick the standard one. Okay. So, let me choose. This is one of the exercises given in the lecture notes. Find the unit normal, find the unit normal and equation of tangent plane. For the sphere, x square plus y square plus z square equal to 1. So, we are given a sphere with center at the origin and radius equal to 1, and I can convert it into implicit form. At what point? So, at points, at the point, you can consider various points. Number 1, I can take the point 1 0 0. This point lies on the sphere. You can also consider tangent plane at the point 1 upon root 2, 1 upon root 2 0. You can see this lies on the sphere, and you can also consider some other points like 1 upon root 3, 1 upon root 3, 1 upon root 3. So, one can draw a tangent plane to all these points on the sphere and work out the equation of the tangent plane. So, solution is straightforward. So, I can write down a function f x y z as x square plus y square plus z square minus 1 equal to 0. You can see the left side is a function of 3 variable, right side is 0. So, this equation is in the implicit form. So, what I need, and the tangent plane is given by this box equation. So, let me choose this one. Okay. So, x 0 is 1 upon root 3, y 0 and z 0, they are also 1 upon root 3. So, I have to work out only f x, f y and f z. F x means partial derivative of f with respect to x, that will be 2x, and this implies f x at the point 1 upon root 3, 1 upon root 3, 1 upon root 3, that will be 2 upon root 3. Okay. Similarly, f y is 2y, and this means f y at this point will also be 2 upon root 3, and f z will also be 2 upon root 3. F z at this point will also be 2 upon root 3. So, normal you have found. So, the normal, unit normal to the surface at this point will be 2 upon root 3, 2 upon root 3, 2 upon root 3, and to 1 upon how much? 12 upon 3, 12 upon 3. No, this will be 4 upon 3 plus 4 upon 3 plus 4 upon 3. So, how much? 12 upon 3 means the square root of 3 for the 12, just 2. Okay, so 2 upon root 3 you take common, 2 is cancelled out, so you can write down the unit normal. So, you can simplify it. So, this is the unit normal.
This type of problem they have done in advanced calculus, where only they explain this thing like this tangent plane can be considered as a level surface.
Yes.
Y z is equal to 6, so one is a constant, and then they have a same equation.
Same, yes, that's also correct. Yes, same.
Level surface.
Yes, you can consider it as a level surface also.
So they have explained this.
Okay, this can be one of the ways. All right, that is also correct. And then we can now we have to find the tangent plane. So the tangent plane is given by the equation x minus x 0 into f x 0 plus y minus y 0 into f y 0 plus z minus z 0 into f z 0 equal to 0. This is the standard equation of the tangent plane. So, in our case x minus x 0 is 1 upon root 3, f x 0 is 2 upon root 3 plus y minus 1 upon root 3 into 2 upon root 3 plus z minus 1 upon root 3 into 2 upon root 3 equal to 0. Just simplify it and you get the equation of the tangent plane. Okay, so computation I am not going into. Now there was another interesting problem here, and this is if all the normals of a surface pass through a fixed point, then the surface has to be a sphere. You can visualize all the normals of a sphere pass through its center. But this is true the other way around also. If you have a surface which has this property, then that surface will be nothing but a sphere. So, this is our next problem. Show that if all the normals of a surface pass through a fixed point, then the surface is a sphere. Yes, it will turn out to be the center, but you can take a general point. Okay. All right. So, suppose I have this surface in the space R3, and it has this property that all of its normal, whatever point you choose, all the normal pass through this fixed point. This fixed point I will call as capital R0. If I draw normal over here, then once again this normal pass through this point. Normal over here also pass through this point. Normal over here pass through this point. Okay. So, these are the normals. They will never look like this, but I have drawn just to show you what is happening. So, well, एक बात आपको समझनी चाहिए कि अगर आप सरफेस पे मूव कर रहे हैं मान लीजिए पॉइंट P से पॉइंट Q तक आपको जाना है. So whenever you will go, you will choose points, they will turn out to be along certain curve. Whenever you will move on a surface, you will notice a curve is automatically drawn. Okay? So that curve I will call as R equal to Rs. I will consider a curve in its natural parameter. Okay? And these points which I have taken arbitrarily are along the curve. ऐसा भी हो सकता था कि एक पॉइंट यहाँ चूज़ किया, यहाँ किया, एक वहाँ किया, एक वहाँ किया, और डिस्क्रीट भी हो सकते थे. बट वंस आई प्रूव इट फॉर ए रेगुलर कर्व, it will be done on the entire surface. Okay? So I will automatically, a curve is drawn and this curve is R equal to Rs. Okay? So what is happening is now look at this. Suppose this is the curve on which we are moving Rs. Okay? So this point, suppose I choose this point is Rs. Okay? And this point capital R, the position vector also I assume as R0. So Rs minus R0, if you look in the figure, will be what? Will be this vector. Is it right? Now this is a vector which is along the normal. Its size may be different, so it will be some lambda times the unit normal. Okay. Since the unit normal from point to point will change, I will call it Ns, and this distance will also change, the length will change from point to point. So lambda will also be a function of s, but this is a scalar valued function and this is a vector valued function. So n is the unit normal. Okay. So Rs minus R0 is this. So this is the first thing to realize. Okay. Now what I will do, I will differentiate this. So differentiating the above relation with respect to differentiating, in fact there are, you know what you have to do, and you also know what is the equation of a sphere. Once you keep the equation of the sphere in mind, you can decide from the beginning how to approach this problem. So if a sphere has a center at the origin, its equation is mod r equal to constant. If the equation of a sphere if the center of the origin, center of the sphere lies at r0, its equation will be r minus r0 equal to constant. So these things are in my mind. Before I approach this question, these things should be in our mind. So what I will do, consider the derivative of, consider this derivative d by ds of modulus of Rs minus R0, okay, square. Okay. This is number 1. I am considering the derivative of this. This I can write down as d by ds of Rs minus R0 dot Rs minus R0. Okay. All right. Now, how will you differentiate with respect to s? By parts. So derivative of the first term, that will be r dash s. Derivative of this will be 0. So only this much, dot second as term as it is, minus R0 plus the same thing. So this is 2 times. or I can say you have 2 times R s minus R 0 dot the tangent of the curve, the tangent of the curve over which you are travelling. All right. Now, R s minus R 0 from relation 1 is lambda s into n s. Okay. So, this is 2 times n lambda s dot n s, no, not dot, this is a scalar multiple, dot t. Okay. Now, n will be perpendicular to t, because this n is normal to the surface at that point and t is tangent at that point where you are staying. So, their dot product will be 0, the reason being because you are computing tangent and normal at the same point. So, this product is 0. So, what turns out is that the derivative of this quantity is 0, and therefore, this quantity must be constant and we are done. So, the final,
We have to keep in mind this thing.
yes.
Otherwise,
Okay. So, what you have is, so this implies mod of R s minus R 0 whole square is a constant, and this implies mod of R s minus R 0 is constant. Okay. And this is the equation of a sphere. This is the equation of a sphere. Which sphere? Whose center is R 0, whose center is a point whose position vector is R 0. So, you can write down the detail by yourself. So, the overall imagination should be there how to go about it. All right. Okay. Now, I stop at this point because in the next lecture I will discuss something new, that is the first fundamental form over the surface. So, we have a rest for 5 minutes.